Our next talk is Leanne Powell. She's a student of Dr. J. Kim, and she is going to talk to us about differential equations.
Yes.
Right?
Hi, so just a little bit of an intro. I'm Leanne Powell. I took differential equations last semester with Dr. J. Kim. For one of our big projects, we had to do one of the project problems from the book, and I picked this one. So it goes through 3 different problems where we look at nonlinear differential equations that are missing variables, either they're independent or they're dependent variables. And so we developed some pretty clever methods of solving these so that we can use first order techniques, which if you're familiar with solving equations, is a lot easier than any of the other ones. So we use this substitution where we use let w equal the first derivative with respect to of y with respect to x. So using that, we can use the first derivative of w for the second derivative of y. So what I just said. So if we're missing our dependent variable, we let w equal y prime and w prime equal y double prime. So we get these nice little equations, and it makes everything flow pretty seamlessly. So if we had this equation, by the way, the fun stuff's at the end, so I'm going to breeze through this because no one wants to sit through a 10-minute math lecture. So we use this substitution on this equation, and it actually made the problem really easy. It was only like maybe a page of lines of work. If you want to see the work, you can see me afterwards. So then for missing independent variables, we let w equal dy dx, and using a fun little chain rule, you can get this substitution for w dw dy equals d, the second derivative of y. And so now y is playing the role of the independent variable as well as the dependent. So we can get w of y instead of y of x because x is missing. So we solve these equations, several integrations, lots of work, a lot of work, and we get this nice equation to our differential equation. And like I said, I have all the work in the back. If you're interested, you can come see me. So all of this helps us figure out this awesome curve that's called a catenary curve. So a long time ago, back with the times of Galileo, we're looking at the stars, conic sections. They see a chain hanging between 2 points and is suspended completely on its own. And they think, wow, I think that looks kind of like a parabola. So they look at it and they determine maybe not so much. So later on, we get to Leibniz and we get calculus, and they determine that it is not a parabola, it is a catenary curve. And the really cool thing about this is that for each link, if you think about it as a chain, each chain in that curve is going to have the same forces acting on it, the whole curve, which is really, really cool. So this is used in so many applications. Like if you invert this curve, you get arches. So like the main page was St. Louis Arch. It's used in architecture. So they can determine the tension forces and compression of how they can make that arch as stable as possible through the whole curve. So these are kind of like suspension bridges. The only difference is that they're not completely catenary curves, but they have a similar foundation to them. So they come from these 2 equilibrium equations, and that top one is the one I had to solve for the problem, that's the differential equation. So that'll give you the tangent line for each point. So you get these 2 equilibrium equations, and the horizontal component is the tension force, and it's always going to be constant. It's going to have the same tension for every single point on that curve. And so then we get this fun little constant, this 1 over a that you see. That gives you all of the forces that are acting together on that curve. So rho is going to be the density of your material, g is your acceleration of gravity, and a is the cross-sectional area of the thread, so whatever area that you're looking at. So it accounts for your gravity, it accounts for the material. So you can see how this is really important when you're looking at architecture and physics. So we see that this A, you can see how that is affecting your curve. So for your bigger A's, you're gonna have this more wide kind of looking curve, and then the smaller it gets, the more it's stretched out. So you can see how this one kind of looks like the St. Louis Arch if you flipped it upside down. So it can be described by the hyperbolic cosine, which is easier than looking at the e to the negative and all that fun stuff. But what's really cool about it is that it's uniquely determined by A, which is its parameter. And this is going to have one more side in here. Is it going to click? And it's going to freeze. And I think there's a video, but I'm pretty sure it's not going to play. And it's not responding. Okay, that's fine. So the next slide was just going to be a cool video. So what's even more interesting is if you take this curve, maybe you can imagine it in your mind, maybe you're good at 3Ds.
Okay.
And that's the end of the video. So if you take that curve, if you rotate it around the x-axis, you get what's called a catenoid. And this is really cool. So you know how every single point on that curve has the same forces on it. So the catenoid is one of the only surface of revolutions other than a plane that is going to be a minimal surface area. So for every curve, and when you rotate it around the x-axis, you're still going to get a minimal surface area surface. So you see that in soap films. Do y'all ever play with soap, like bubbles as a kid? You pull the rings apart and it has the soap in the middle. That's what this video is supposed to be. So that's a catenoid. So they found that that catenoids are soap films because when you rotate them around, they get the forces from the outside and the forces from the inside. And the further you stretch it apart, it determines that the minimal surface area is no longer when it's connected, it's when it's pulled apart. So then you get these two separate planes, and all of that force and pressure, you get this nice little sphere of a bubble in the middle, this cute little bubble. But it shows up in nature because it is a minimal surface area because of its base curve. Not getting so much fun. Any questions?
It's play. Is it loaded there finally?
It doesn't have a play thing on this screen. I don't know. Oh, maybe it will play.
Let's keep our fingers crossed.
So when you're watching this, watch for you can see it. So it's a really high-speed film. I think they said it was like 1,000 still pictures or something like that. So you see these curves. As they pull it apart, it gets stretched out, and that A parameter is growing. And then, there we go. So all of that energy is released, and you get this little sphere. That's pretty cool, right? Like, I freaked out. Like, when I saw this, I freaked out. But that's just
Very nice.
looking.
Okay, glad to